Okay, so thank you all for coming. I'd like to go ahead and get started. So my name is Drew.
What's your name?
Andrew.
Oh,
For those of you who don't know me, I'm very excited to be able to give this talk. This talk is for my master's thesis, which was obviously like last year. Actually, this is work that was done in like 1999. So when I was preparing to give this talk, I was searching in my house for these things called CDs because I had backed stuff up, and at the time CDs were cutting edge because a lot of this was originally on floppies. So I managed to pull it together and do some slides, and it's kind of interesting, I think, for reasons that I'll get into. So just to say that this is a replication I did for my master's thesis. I actually did a bunch of additional new work, but I won't be talking about that today, so I can just focus on the replication issue. Okay. But if you ever want to talk about any of the rest of that stuff, I'd love to talk to you about it. All right, so gradient descent into chaos. What does that mean? So my master's thesis was involved with recurrent neural networks. And if you don't know what those are, I'm going to spend about the first half of this talk unpacking that. And it turns out that in certain situations, the state space of neural networks, which I will unpack later, exhibits fractal dynamics. And so you can see here for one of my networks, as it learns, it's got an x-axis for one hidden unit, y-axis for another hidden unit, z-axis for a third hidden unit. Together, these create a state space. And you can see the evolution of this over time becomes a kind of fractal dimension attractor. Now, are there any mathematicians in the room? Okay, so I'm going to throw around a few terms like this periodically, like chaos and fractals and stuff like that. It does turn out that with this work, like someone went and showed that this really does have fractal dimension like properly. So don't worry that I'm not just saying it's a fractal because it looks like one. I mean, it's not. Okay. All right, fair enough. So what is this? It seems really interesting, right? It seems like it's doing something magical, right? That was the intuition, I think, that led to this person, who I'll introduce later, to publish a paper claiming that it was doing something magical, and I actually found out that it was not. So the theme for this semester is replication, and as was been raised, I think, in some of the previous talks, there's different kinds of replication. There's different ways of thinking about replication. So one way of thinking about replication is a direct replication, and you wear the same shoes or even the same socks. You want your socks to be the same color, right? You want to put them on in the same order that the original experimenter put on their socks, okay? Very, very direct.
You want your feet to be the same age.
You want your feet to be the same age, right? You want to wake up in the morning and face the same direction. So if it fails, if you do a direct replication and you're really very direct and it fails, then what do you learn from that? So you might think, oh, well, the first experiment was some sort of type 1 error. You did exactly the same thing, okay? And if it succeeds, maybe you think that the first thing was right, okay? You increase the probability that it wasn't a type 1 error. There's also this conceptual replication where I would describe this as testing the same hypothesis. And if it fails, then maybe the first result was an error, or it really lacks this kind of external validity. It just doesn't generalize the way that people thought it generalized. And if it succeeds, then maybe the first result was right and it has this generalizability that we all hope for, okay? What I'll be talking about today is actually something different, right? It's neither one of these two things, which is why I'm introducing them. So today it's a successful direct replication, which is easier to do when you're doing computer models and neural networks and stuff than it is when you're dealing with people, right? Because you can't do the replication with the exact same subjects that the first experiment had. But even though I have a successful direct replication, I find a problem. And the problem is that the causal relationships originally assumed, or the interpretation of the original results, turn out to not be correct, I would argue. So to kind of put this on a footing with which I think a lot of people are familiar, you can find all kinds of spurious correlations in science. This, you can't quite read it, but it's tylerbingham.com. He has a whole website of these things, okay? So, I can show that per capita cheese consumption is highly correlated with the number of people who died by becoming entangled in their bed sheets. Okay, and you might even think, oh, well, I should build a causal model of this because look at that relationship. That looks pretty good. Or what about this relationship? Letters and winning words of Scripps National Spelling Bee and the number of people killed by venomous spiders, right? I mean, that looks pretty compelling, right? But we know that there are all kinds of just nonsensical correlations in the world that could just be due to chance. There could be some third variable that's influencing these. There's all kinds of reasons, right? But sometimes when we do research, we may impute causality where there is in fact no causality, or misunderstand the process that gave rise to the data, and that's what I'm going to be talking about today. All right, so here's an outline for the talk, and I'm doing my best not to lose anybody. But I'm gonna start off assuming that most people don't know what a classifier is, anything about neural networks, et cetera, before I can get to this thing at the end. So I hope you'll bear with me. Okay, so what is a classifier? A classifier is basically a function. Put something in, you get something out, right? The function usually does something. So a classifier, you input an item, and you output a category or a classification, okay? So the simplest case is a binary classifier. You have two categories, right? There's two things that your input could be. So one example of this is a thermostat. So you've got temperature measurement input. Your temperature, I put next there. Temperature X is compared to threshold T, so that if X is greater than T, right? My temperature is greater than my threshold, then I'm going to cool. If my temperature is less than my threshold, I'm going to turn on the heat. This is an example with which I think we're all familiar. I did make that a little bit dirty because you probably have a cool heat switch, but whatever. Let's assume that your air conditioner or heating is better than mine. And what happens? So either it does nothing or it does something in terms of the activation output. It heats or cools. So you can think about this as one dimension. You have a threshold. If things are below the threshold, it turns on the heat. If it's above the threshold, it makes it cool. Okay? Classifier. Two-dimensional classifiers are a little bit more interesting. In this case, typically you have a linear classifier. You've got two, but you can't see that. You've got two outputs here, blue and green, and you try to separate them with some sort of line, or potentially it doesn't have to be a line, but in linear case, it's a line. So you typically have two measurements on the input, like this dimension and this dimension. You still only have two output categories. The decision boundary is now aligned. And here's an example. So assume that I've got two measurements on a thing, right? I've got one of these input items. One is a measure of animalness, and what is a measure of foodness, okay? And the classifier is supposed to decide, is it animal or is it food? Okay, I know that I'm a vegetarian, so I actually make a distinction. You may not, but you probably will in these cases. Okay, so I got my animal dimension, I got my food dimension. Animal or food. This is a game. You're allowed to enjoy this. Animal or food?
Animal.
Okay, so that's our little red dot for animal. It's fried chicken. Very good.
Animal.
It's animal. This is one of those wrinkly-faced dogs. Sharpays, as the French say.
I get it pretty live. Chicken was an animal. Oh.
It's a marshmallow. Okay, so I've made this a little bit funny, and I've abstracted like the computer vision task that's really here. But if you can imagine that we've got these two dimensions, then we might end up with this kind of space of features, and we might be able to draw a line between them and discriminate. Okay, so that's and all the stuff I'm going to be talking about today. That's really the basic idea. Okay, and the neural network example I'm going to focus on later is basically this exact kind of thing. Okay. So for those of us who are familiar with regression, I may have some sort of animalness measurement, some sort of foodness measurement. And I basically just form a line, right? So I've got an intercept here, like this is B. I've got some weights that decides how much I weight these things, and now I've got regression. Okay? Ta-da! Basic neural networks. So neural networks you can actually think of as regression, and that gets you really far. Okay? So if anybody's familiar with regression, who in here is familiar with who in here is familiar with regression?
Who is or
Is familiar. We've at least heard of it. Okay, and everybody here knows the equation for a line. Y equals mx plus b. Okay, regression. All right, so here's a neural network that does exactly the same thing that we were looking at with animals and food. So we've got some sort of animal measurement, we've got some sort of food measurement, we've got some sort of bias that we learned, and we're multiplying it by some kind of weight, okay? And so then we end up in our node here with some of these values, and we just sum them, right? So we just put pluses in here, and we get that, okay? Yes?
What's the 0, 1 represent here?
Oh, it's just a measurement from 0 to 1.
Oh, okay.
Yeah. Maybe it should have brackets or something. So you can think of a node in a neural network is doing this thing where it's taking some inputs, and if it's a linear sum, right, it outputs a regression formula, okay? But it turns out that in most cases that people are interested in, for reasons I will explain in a second, that neural networks actually do more than regression. So if you just sum the inputs, right, then that's linear, and that's like regression. And that looks something like that. Actually, sorry. So, or you can actually transform the sum, right, in a nonlinear way, and then you get something else. And so this is an example of a nonlinear transform. So this is the sigmoid function, okay, which I think I'm going to give a picture of.
Same one you use in logistic regression.
In logistic regression, that's correct.
So now we're at logistic regression.
Yeah. This is logistic regression. Yeah. So I actually have a picture later, but for those of you who aren't familiar with the sigmoid, it looks like, sorry, S's are so bad. We do it backwards. There we go. It looks something like that, okay? So plateaus of 1 and at 0. Okay, great. So in neural networks, they typically do something like this. So it's no longer just this linear sum, but they force it through this nonlinear function. Well, why do they do that? Well, the reason is that if you do that, then you can stack these nodes together and make them do something interesting. So layers of these nodes, so let's say that this is my first, animal food node, right? And maybe I've got like a different one up here, and these both feed into this one, like, right? That's what layers are. If I've got layers, then they're just compositions of functions. If I have linear compositions, then it's just linear. And I could have done it with just like one layer, okay? But nonlinear compositions are very useful. I'm going to give an example of that in a second. And instead of getting into the math of this, I'm just going to do a demonstration to kind of help make the point that if you just stack a bunch of linear things together, what you get is linear. But if you stack a bunch of nonlinear things together, you get something that's, different. Okay. So this is a classic example, and I do have the sigmoid here. This is a classic example of a non-linearly separable problem. So if you have a bunch of linear nodes, you can't do this because there's no way that you can draw this boundary and make all of the blue dots on one side and all the red dots on the other side. It is no longer linearly separable. But if you have a neural network with nonlinear activations and multiple layers, you can do this. So let me show you an example of this. So here's a linear example. So I think people in here have probably heard of Google. So Google and some of these other tech companies have started open sourcing some of the stuff that they use. Google has something called TensorFlow. TensorFlow has a GitHub repository. They have this really nice playgrounds that you can mess with and do things. So it's a little bit smaller on the screen than I realized.
So Andrew,
yes.
A terminology question. I see a lot of papers on tensor mathematics. Are they just giving another name for current neural networks then? Or is there something essentially different when you're talking about tensors as compared to neural networks?
So tensors are like a generalization of, so the way that I would say this, which could be wrong because I'm not a mathematician, is that tensors are a generalization of matrices. So when you normally think about a matrix, you might think about a matrix like in 2 dimensions, whereas a tensor you might think of as a higher dimensional matrix. That's the way I would describe it. Does anybody have a better way? Okay, because I'm not an expert in tensors. Okay, so here's our problem that we were just looking at before. We've got red dots and blue dots. We want to do a decision boundary between them. We have 2 input nodes right here, and if I come over here and it's linear, so I've got 1 layer here, and I'm going straight to that. And if I run this, yay! It learns the line between the 2. Okay, so that's fine. And I can actually come over here if I want, and I can add some more hidden layers, but I'm not actually achieving anything. I'm getting the exact same result I was getting before, because when I compose these, it's just all linear. Okay. Or I can come over here and I can do one of these that's kind of interesting. So now I've got my 2 input nodes. Now I've got a problem where all the blue dots are in the middle and all the red dots are on the outside. Okay, there's no way that I can draw a line that puts all on one side of the line. Okay, what I need to do is actually draw a circle boundary in between those 2. And I can do this with 3 hidden units, although it's a little bit harder for it. So it's going to struggle for a little bit. So you can see it's trying to do 2 lines. What it really needs to do is do 3 lines. Come on, buddy. Yeah! So you can see, and actually, I don't know if you're paying enough attention, but it actually was very circular for just a second before it became triangular. You can make this easier to solve if you add a bigger hidden layer. So, you know, and if I get rid of these, right, it's kind of like oh, yeah, here we go, sorry. If I get rid of these, then this is what we were saying, and there's no way that it can draw a line, okay? So that's the basic idea, and I don't think it's possible with 2. I think you need 3. All right, so that kind of gives you an idea, okay? So we're talking about these neural networks. In order for them to do things that are actually really interesting, we need layers, okay? And they have to have this non-linear thing, which is this sigmoid, which is squishy, right? It's going to squish stuff. All right.
Can I ask one
Yep.
from the nonlinear? 2 of the problems that people talked about with neural networks and their power is the XOR problem
Yep.
and the parity problem.
Yep.
Are you going to address that?
I'm going to be talking about parity,
Okay.
which I've defined as sequential XOR,
Uh-huh.
is that the way historically?
Okay.
So it's the same idea as XOR, but it
Okay,
takes a sequence of inputs.
Okay.
Yeah.
All right.
So the first thing that I showed, where it was like 2 blue dots and then 2 red dots, not the first thing, but the one I said first time I said linearly separable, that was XOR, or one depiction of XOR. Okay, so, you know, I just ran these demos, right? And it started off and the networks hadn't learned it. And then, you know, they were learning and all of a sudden they had a solution, right? So what happened behind the scenes? So the way you learn with these things is you start off with a random initialization of these weights, okay? And you remember I had like, you know, the linear regression, the weight was the thing that I multiplied by animalness or foodness, right? So just like your slope in a line equation, okay? So start off with that just being some random junk, usually between -0.5 and 0.5 or something. Okay, then for every item that you're trying to learn, you run it through the network and you calculate the output. It makes some sort of class assignment, right? It's animal or it's food. But sometimes it's wrong, right? If it's wrong, then you compute the error, which is the difference between what it output and what you wanted it to do. And then you change all the weights in the network proportional to how much they contributed to that error, okay? So if they contributed a lot to that error, you want to change them a lot. If they contributed very little to that error, then they're probably good weights and you don't want to mess with them, all right? That's the basic idea. And then you just basically repeat that process by going backward through all the layers, okay? And that's called backpropagation, and it is a kind of gradient descent. And without getting into all the math and stuff of it, which it's kind of good to know, but you don't actually have to know it to appreciate what it's actually doing. The classic example is, I'm on a mountain, and it is cloudy. And I'm trying to get off the mountain or I will die. Okay, so this is like, this is what you're doing to your poor neural network. It will die if it does not get off the mountain. So, so you may be starting at the top, right? This might be your peak error, right, up here. And it's all cloudy, it's all foggy. So what strategy would you use? You'd probably look at the ground, which you can see, and look around and say, oh, where do I have the best slope here? Where can I like maybe go down the fastest, right? And you say, oh, gradient looks good over
Watch
here.
out for cliffs.
Yeah, watch out for cliffs. Yeah, not that fast. Oh, the gradient looks good over here. I will go this way. So you go over here. And then you're like, okay, now where do I go, right? And hopefully you don't turn around and go back exactly the way you came. Hopefully you kind of make progress. And that's exactly what gradient descent does. It just defines this error, which you can think of as a surface, and it just follows the path down the gradient to minimize the error. It's an algorithm that just uses local information. It doesn't have a global view of everything, okay? That's pretty much all you need to know for this talk. All right, so we just did classifiers and neural networks. Now let's do sequence classifiers, okay? What is a sequence classifier? A sequence classifier is exactly like a classifier, but the difference is instead of just putting in one thing and getting something out, now I'm going to put in a sequence of things and get something out. Okay, so it's a sequence that I'm classifying. Okay. So the simplest case that I can think of is parity. So parity is like evenness or oddness. Okay, so an example is odd parity. So if I have two kinds of input, I can input ones or zeros, and I input a sequence of ones and a sequence of zeros. I want the classifier to tell me if the number of ones is odd or not, right? So if I input 1, 1, 1, how many was that?
3.
Is 3 odd? Then it should output 1, which means yes, right? So 1 or 0 is like yes or no, okay? So that's what it's doing. If I had an even parity 1, then it should have given me 0. It doesn't really matter. We're just going to stick with odd parity so it doesn't get confusing. So the classic way that computer scientist people think about this problem is that you have two states. So you start off in state A, right? Which means it's even parity. If you see a 0, you just stay here. You're like, oh, I'm seeing zeros, everything's even, okay? Then as soon as you see a 1, you go, oh, I saw 1, now I'm in the odd parity state, right? If I see a 0, oh, I just stay in this state, right? Because I'm still odd, right? Seeing zeros doesn't change whether I'm odd or not. But as soon as I see a 1, uh-oh, now I'm even, now I'm back over here, okay? So it's a two-state machine, and then at the end of it, you basically say, okay, you know, are we here or are we here? If we're over here, then it was odd, and if we're over here at the end, then we're even, okay? So that's a classic way to do this. We will not be doing it this way, but I just wanted to give you that example. Okay, even or odd? Nice, very good. Did you do that by memory or did you actually count it?
Rehearsed it after.
Remember, remind me to never play cards with you. All right, so you can imagine that first task where we're doing this one at a time. We just do a sequence of this and we get an output, right? That's the only thing that we've changed about this problem. Now you know everything you need to know about sequence classification. Let's do recurrent neural networks. All right, so you guys read Elman for the class, right? Okay, so Elman is has a very classic paper on recurrent neural networks in cognitive science, and his model looks like this. Okay, now before we get into that, the first thing to think about in this sequence problem, right, is that you need to have some sense of history. Okay, you need to know if you've seen animal or food before in order to be correct. You basically have to count them, right? Maybe you just need to remember like what your last kind of state was or whatever, but in some sense you have to have a memory, okay? How would you do that in a neural network? Because straight shot neural network, what we were looking at before, it just goes this way, right? So everyone I see, I just map it through, right? This is my function. I'm just shoving this stuff through. A recurrent neural network does this history thing in multiple ways, but it's always by recurrent connections. So basically, you always have some of your input from time t gets split, comes back here, and is seen again at time t+1. And that's exactly what this is. It's like I put something in, it hits the hidden units, it splits, it goes out, and I get my classification at that time. But the part that splits comes back here, and when I insert my next thing in the sequence, it comes in together and makes a kind of joint decision. Like, so given the current input and given the history, what do I do? Okay?
Question?
Yep.
This seems really busy, like updating your priors.
I haven't really thought about that. I think that you could, consider it in that kind of framework, but I haven't, so I don't have anything more intelligent to say. But it is, this stuff, especially the straight up neural network where it's firing through like this, you can understand that almost entirely in terms of statistics. What gets kind of interesting is that when you start having recurrence, it becomes kind of a dynamical system. So that's foreshadowing. So yeah, I'll think about that. Okay, so what are the cool results from Elman? I'm just going to throw up here on a slide so that the students feel good that they actually read that paper, which I'm not going to talk about anymore after this slide. One of the really cool results he does is he constructs these sentences. They're like sentences of English. He uses a really simple grammar. You can't see that, but that's his noun. So I might have like, a human noun, and then I might have like verb eat, and then I might have noun food. So, the man eats chicken, right? And he just generated a ton of sentences like that, but using this kind of template. So sometimes it was the man eats chicken, sometimes it was, the animal sees a human, it was whatever sort of mixture of these things it could do. And he fed all that through the neural network, okay? And what did the neural network learn, okay? So what happened was the neural network, he was training it to predict the next thing in the sequence. The neural network actually learned a kind of clustering of these items. And you can look at this as a kind of categorization that it did. So I don't know if you guys can see this, but like right here it says food. So sandwich, cookie, bread, sandwich, cookie, bread, that's food. And then breakables are plate and glass. And here you've got car, book, and rock, which is obviously an error. But for human, you've got woman, girl, man, boy, et cetera, et cetera. So it's kind of like this almost like little ontology that it learned from this input that he gave it. And so people looked at that and, I think very appropriately, they thought that was pretty cool. Yeah.
How do you extract the ontology from the network?
So I don't remember specifically how he did it right now, but since he did it on a prediction paradigm, one way that you could do it is look at what it was predicting would happen next. And things that are close to each other in space should have similar predictions. So he might have done it that way, or he might have done it the way that I'm going to show you that I did it later, which is you just look at the hidden unit activations. And you use the hidden unit activations, which are basically like a vector, and then you just cluster the vectors together. Does anybody remember any of the students who read it for today? Because I haven't read it in a while.
I remember doing this back in '97.
Okay.
With speech act classification, and I seem to remember, this is the one finding structure and time.
Yep.
Yeah. And,
Classic.
I thought he did look at the similarity of the hidden layer vectors.
Okay.
Yeah.
Okay.
That's what I remember.
I believe so,
So-
having just read it as well.
Great.
Saw the word vector.
So there's two, as far as I know, there's two classic ways of doing it. One is off the hidden units, which is what I'm going to show you, what I did, and I'm going to show you later. And then the other is looking at the prediction error at the output, because he used a prediction paradigm. So that's not always available. Okay, so what's really happening here, right? Because you look at it, and you're like, oh, the neural network, it's magical, it's it's learned all these things. Really, what it's doing is a kind of recency clustering, I would argue. So it's clustering things based on the most recent input. So when it says, hey, I think this is food, it's like it's got all these kinds of food and it makes the same kind of hidden unit activations. It's because the thing that preceded all of those kinds of food was something like the verb eat, right? And it just so happens that I'll just say this, and I can get deep into it if people want. It just so happens that in English is mostly right branching. So that it's really easy to get recency clustering in English because of that property. So, okay, and this kind of happens because of the gradient, right? So I was talking about the gradient before. Okay, so you've got this gradient that allows you to see back in time and look at your history. Okay, because every time the neural network runs, it's basically shoving stuff through the sigmoid, and it's kind of squishing things, right? And so things are getting kind of more and more vague as it iterates. So what happens? Just what happens when you multiply numbers that are smaller than 1?
Let's get smaller.
You get a really small number. So that's exactly the problem here. So if you take the derivative of the sigmoid function, so actually the derivative of this is that. So the derivative of the sigmoid function is highest when its input is 0, okay? And its highest is 0.25. That's okay, I thought somebody was asking a question. So when you actually do this like magical backpropagation stuff, you end up with something like this, where you're taking the error at the output unit and you're trying to attribute it back in time to all of the weights that were responsible for that error. And when you have a recurrent neural network, basically what you're doing is you're unwrapping it. So if I put 4 things into it, you can basically think of that as a neural network, and then at a different time unwrap it, and then at a different time unwrap it, all the way back to the beginning of the first input. You could try to push the error all the way back there. But the problem with it is that this number, this derivative of the sigmoid, at best, it's going to be 0.25. It's actually something different than that, but it's basically that idea. So every time you go back 1 step in time, it gets smaller. Your gradient gets smaller. Your ability to figure out which direction you should move in gets smaller. So you can make very tiny weight adjustments. So what does that mean? That means you can make your biggest weight adjustments going back 1 step in time, which gives you recency clustering. Okay.
So this is due to the persistence of the context is much less if it goes through that cycle a few times.
Right. Right. So you can only, if you're using gradient descent, you have to have a gradient. If you're using a different learning algorithm, it wouldn't be as much of a problem. But if you're using gradient descent, which is the classic thing that people use, you have to have a gradient. And the gradient gets really small the further back in time you go. It just gets smaller and smaller. Okay, so is recency clustering enough? Hey, maybe recency clustering is all we need, right? All you need is recency clustering. Well, it turns out that, for a lot of long distance dependencies that we are interested in, you can't use recency clustering. So here's an English example. The first woman who flew in space was Sally Ride. There's all this stuff in between woman and was, but woman and was are linked by subject-verb agreement, right? So, they're both singular here, right? So you would screw that up if you couldn't connect those pieces arbitrarily over time. I can make that really big. Here's another example for parity. I see a 1, right? So it's odd. Then I see like 20 zeros. It's still odd, right? I have to be able to remember that I saw this 1 regardless of how many zeros I see. So I need to latch on to that information in order to solve this problem. So recency clustering isn't really going to do me for that. I promise you I'm going to bring all this back together like almost now. Okay? So now we have all the background we need to understand my replication. Does anybody have any questions? Okay. So this guy had this really cool paper, which I encourage everybody to read. His name is I think he's still alive, Pollocks. He did this paper in '91. It was in the Journal of Machine Learning, which I think was like in its, I don't know, like 4th issue or something back then. And he had this really provocative title, The Induction of Dynamical Recognizers, right? Very provocative. He made a number of claims. The first is that when you talk about these recurrent neural networks, learning takes place via a phase transition, right? And I'll show you what that looks like in just a second. But basically, in a dynamical system sense, he's trying to equate a term in dynamical systems theory with learning, which is a pretty cool idea. Another is a claim that he makes is that in theory you could exploit the fractal dynamics of these neural networks to solve really complex classification problems. If you have a question about that, I can answer it, but I don't want to get us bogged down in what exactly that means right now. That's a claim that he makes, which is also very cool. And one of his test cases is odd parity, which I'm going to talk about for the rest of the talk. The other test cases are the Tomita sets that he used. That's actually that movie that I showed at the very beginning, like that. That was one. I think that was. Oh, actually, it's off the slide. That was, I think, Tomita 7, and I'm not going to talk about those because they're just so much more complicated. But it's basically the same setup as odd parity. So I think if you can understand, if you follow the odd parity example, you can see that it holds. The replication problem holds for the rest. Okay, so he had his very own special recurrent neural network, and I'm going to start making like little snide comments, but this is cool work, and I don't want anybody to think that I'm just trashing it because replicating was really hard. One of the reasons that replicating was hard is because no one else uses this but him, right? So if you do like a literature search, like this is his thing, and it was not really imitated, okay? So oh, I think maybe I just ran out of, did I go to sleep?
The cursor's there. So
The AI is alive! It's taking its revenge.
Who is it? Is his name Jordan Pollocks?
Jordan Pollocks.
Yeah.
Do you know him?
Yeah,
Okay.
I remember from years ago.
He's at Brandeis.
Yeah.
Or he was at Brandeis.
He's there.
Okay, cool. Uh-oh, you're not tweeting this talk, are you?
No, make sure.
You're gonna get really angry call from
Maybe.
Jordan.
Maybe he is really.
Let me just do this. Sorry about that. I'm not entirely sure. Oh, show recovered files. Yeah, how about this one? Sorry about that. Technical glitch. Yes. Click it. All right. All right. Okay. That was weird. Okay, so this is what it looks like. Oh, oh now I'm really confused. Hold on. Did you see anything on the screen this whole time?
Now, no, we didn't see anything.
Because it was giving me a graphics card. It was irritated with my graphics card. Oh, wow.
Into the chaos you were talking about.
Yeah. Hold on. Now it's beeping at me. Okay. Still got nothing. That's pretty weird. Okay, I could just reboot. Why don't I do that? I'm gonna reboot. You ready?
Yes.
Oh, update. Oh, I see. It says update and restart.
Oh, my God.
60,000 steps.
And that explains why my video driver was all of a sudden non-functional. Thank you, Microsoft.
It could be quick depending on which update it is.
Could be.
Could be really long if it's put on the other day.
Okay.
So how many are buying the new iPhone? Speaking of budget.
Down with Apple.
Okay, it did reboot. Dook. Need to start giving all my presentations in Linux. Use PowerPoint to make the PDF. There's no animations. Just,
Use Beamer and do it with tech.
yeah, you say that, but
So what did you just say?
There's a package called Beamer that lets you create slides in LaTeX instead of.
Oh, Oh.
So if a lot of your equations and figures are already in a paper for Lithic, it's really easy to swap it out for a fucking slideshow.
I see.
There we go.
I see.
This is my dog.
Food.
Her name is. So, actually, if you came to my house, she would probably say that you were food. But she's a sweetie. All right. Let me see, can I even, oh, that's so great. All right. Now it's finding the driver for the updates were installed. Well, thank you. There we go. All right. This is his own special neural network, okay? Recurrent neural network. He splits it into two parts, which I'll explain in a second. This part he calls the function network, and it's about as simple as it can be, okay? I've got my input, I've got my bias node, which I've been talking about. I've got one layer, right, of nodes past that. One of them is the output, okay? This is really simple. It's almost like there are no hidden units. But then he does something that's a little bit crazy, okay? He has a separate network called a context network. And what he does is he takes these activations and he copies them over here, and then he runs them through some weights to generate these weights that go back into the function network. This is what's called a higher order neural network, sometimes referred to as a sigma pi neural network, although this one is weird even in that category of those things, okay? So
Where does it
basically,
send the vector?
sorry, second.
That vector with all those diamonds.
Yeah.
Where does it send that vector?
So these are nodes, but I colored them and changed the shape
I mean,
to
yeah,
indicate
it's,
that this output becomes this weight.
Oh.
This output becomes that way.
I
This output
see.
becomes that way.
Okay.
That's why it's all color coded. So
Ah,
basically what happens is you start off with some like randomly initialized weights.
I gotcha.
You push something through the function network. The recurrent nodes come back here. And what you're getting the next time around isn't their contribution.
Mhm.
What you're getting is they're defining a new mapping, a new function that then gets copied over here.
Mhm.
So basically, instead of pushing through state, your state is actually triggering a new function. So you're not just sending stuff through the same weights over and over again, like repeating the same function. You're actually changing the function every time you
Gotcha.
push something through.
Mhm.
Yep. What was that question?
Instead of just immediately changing the weights in the feedback connection, separating it from one step, and it creates kind of a delay.
Yeah. So I'm sorry, I glossed over it. So thank you. So like at time t, I push something through, I immediately get an output. This stuff gets copied, new weights get generated. At time t+1, I push something through with these new weights,
Gotcha.
and that's how it goes. So it's in a way it's very much like the simple recurrent network in terms of how stuff flows through. But the difference is that instead of sending through activation through your current nodes in a kind of similar way over and over again, each time you're generating a new set of weights.
Is that the learning part?
This is just what it does when you run it. I'm going to talk about the learning on the next slide. Okay, so this is how he does the learning. So, and actually, I'm sorry, I just realized I reversed the nodes. So this is now the output node. Oh, before it was over here. So you have the output node. So you backpropagate error, right? So this bias one, whatever. You come back here, and these two weights were determined by these nodes in the context set. Then you backpropagate the weight to all of these. Okay. Then you unroll one step. These were your state nodes originally. You backpropagate the weights there, and those are the weights that were defined by your context net one moment before in time, and you backpropagate the weights here. And then he stops, and he calls that truncated gradient descent. As far as I know, he's the only person who does that. So not only does he have a fairly unique, I don't want to say totally unique recurrent neural network architecture, but it's different and not many people use it. He also has a different training methodology. That could be a good thing or it could be a bad thing. So he's only passing error back one step in time. And in a way, that kind of helps with the whole gradient thing I was telling you about. Theoretically, he doesn't have to worry about that as much. Okay, so now we're going to talk about how he uses one of these on the parity problem. So on the parity problem, he used this training data. The fact that I can fit it on a slide is also kind of a bad sign. But you have to remember, he did this original work, I think in the late 80s. And I think people were like, hey, you really should put this in a journal article. And it was published in 91. So, this is way back. So I'm just randomly choosing one. Here's an odd parity string. It's got 3 1s, so it should accept that. Here's an even parity string. It should reject that. Okay? That's it. I think there's 13 examples. Maybe it's 12. Okay. So, what did he show in his paper? So what he showed in his paper was really cool, and he did a lot of stuff graphically. There was a lot of really interesting visualization. Some of it was novel. What I'm going to show you today is not novel visualization, but it was still really compelling. So he trains one of these neural networks using that training set I just showed you, okay? And he's like, okay, check this out. This is what it's doing. I'm going to feed this thing a long string of 1s, okay? Before it's learned this training set, it might look like this, where this is the length of the string. So I fed it here to actually be 1 1, 2 1s, 3 1s, 4 1s, 5 1s, whatever. So for the first couple of 1s that I feed it, it seems to be oscillating, right? But then by the time I get up to like 20 or something, it just kind of hits a fixed point. And it stops oscillating. Okay. You're like, check this out. If I train it a little bit more, I start to get a persistent oscillation. And here you can see that, there's this little one that's probably going to decay way out in the future. But, it's actually now really remembering that that it's seen all these 1s and that, it's even or odd. Okay, now this is the one where it's really interesting. So now basically he's feeding in the 1s, and now it's obtained kind of limit cycle dynamics. And look at what's happened interesting here. So I've kind of glossed over this before. This is the output activation. So if it outputs anything above, let's just say it's 0.8, then we treat that as accepting the string and saying, yes, this is odd parity. If it outputs anything, I don't know, I have to go a little bit higher here. Let's say below like 0.4, then we say, oh, that means that it's not odd parity and we should reject the string, okay? So what he's showing here is he says, in the limit, with a string of 1s, I'm solving this parity problem for an infinitely long string, okay? And you're like, wow, that's awesome, okay? So does that kind of make sense? All right, so.
Well,
Yep.
I mean, it kind of makes sense the way you set it up, but I don't know where he's got the memory for an infinitely long string yet.
Well, so, I showed that finite state automata. So theoretically, you could just have a two-state machine.
Oh,
Right.
it's just alternating back and forth?
You could think that, and this has this alternating dynamic to it,
Oh.
right? I don't think he actually puts that into his paper, but that's the kind of implied thing. It's like, oh, there are 2 states and I'm bouncing back and forth between. Okay, and this is what it looks like. So this is another really cool picture that he made. So this was the length of the string. This is epochs of training, or epoch, however you want to say it. And that just means I've run the whole training set through, I've back propagated error, what does it do? I do that 50 times, I did 100 times, I did 150 times, I did 200 times. So this is basically training, so this is a learning curve, okay? And what you see on the y-axis are these strings of 1s that he's pumping in, but this time he's always pumping in strings of length 25, okay? So with no training, it's basically like, oh, I'm kind of hanging out, all my 1s, all my outputs overlap, because I'm getting the same value no matter how long the string is, and that kind of overlap. And then, oh, wait a minute, I'm starting to get some sort of divergence here, until all of a sudden, boom, it's robustly solving the problem. So this corresponds to this. And the reason that you have these bands here is that these are strings of length 25, so there's a little bit of kind of oscillation wiggle. So that's why you have those. Okay, so he calls that it's a bifurcation, and he's like, this bifurcation is a phase transition, and this phase transition is equivalent to learning. Question?
Just each of those lines, is that a kind of a separate simulation? So he runs it many times?
So each vertical slice is one simulation, but this shows
Yeah. I
all of
know.
the
I'm
output
talking about the
activation
different line.
for the entire sequence of ones. So it's not just like the last output activation, it's the entire output activation. Okay, so I replicated this, right? And here are my pictures. Ta-da! So this one right here, that's kind of weird. That's what it looks like on the very first one you pump in. What does it do with that? That's what that is. So this is the first one, and then the second, third, all the way up to 25 ones. Those become these bands. This is another way of answering your question. Okay, so one of the weird things about Pollocks result on this, it's like, well, how do I really know that I replicated it? Well, I replicated as far as he reported, because what he does in his paper is slightly mysterious. So he doesn't really quantify numerically exactly what happened. He shows a lot. He's like, oh, look, it's qualitative. This is the phase transition, stuff like that. So he doesn't report how often networks learn the training set. So if I start with different initial conditions, how often can they even learn it, no matter how long I run it for? How does it generalize to strings beyond the training set, besides this long sequence of ones? And this, to me, is the most important thing about his claim that induction is like phase transition is induction. Do all networks that learn the training set recognize in the limit, right? And do all networks that fail to learn the training set in the limit, sorry, I'm going to read it the way I wrote it. If networks that fail to learn in the limit can still learn the training set. Because if you're saying that these are identical, these always happen together, then those cases should not occur. But they do occur. And it's so sad when you replicate something and it doesn't work like that. So only 19 out of 100 randomly initialized networks actually learn the training set. Okay, that's not necessarily a damning thing. It's good to report that kind of stuff so people who try to replicate it know, because otherwise they can like run it once and say, oh, it didn't work, I must have done something wrong, right? Not like, oh, I need to run this 100 times and take a sample. Very interestingly, you have 19 that learn all 13 of those training cases, which I'm calling rules here. 76 of them learn 12 out of 13. So 76 of them learn almost everything, except there's one rule that they can't learn. And guess which one it is? 80 networks fail to learn the string 1-1. 1-1 is even parity. It should give an output of 0. But it's the only case in the training set that when the last two elements are 1, the output is 0 instead of 1. And this goes back to this recency clustering thing that I was talking about before. That is an exception to the recency clustering principle. So it looks like what the networks are doing is actually something more like recency clustering. Okay, so, and the weirdest thing about this is that if this is really learning, does that make sense for the networks to get the longer strings right, but to get the short strings wrong? Because the short strings should be easier than the long strings, right? But that's not what happens. What happens is the networks get the longer strings right, reliably, yeah. Okay, so that's kind of weird. How about generalization?
Can I ask a question? Maybe this is the generalization. I'm wondering a different set of beginning, on the training set, a different set of items.
Mm-hmm.
Is this what you're considering generalization?
Yes, so
Okay.
This may answer your question, but bring it back if not. So I said, okay, that's great. Let's put in all strings up to length 10. So that's 2 to the 10 strings, okay, which is really easy with a computer to generate all those, because it's basically counting in binary. What does it look like? So this is not so good. So the misclassification error on this set of all strings up to length 10 is actually greater than the nets that learn the training set.
Error, danger.
Right. So basically generalization is worse when the networks learned than when they didn't learn. Okay. And then this is also a bit damning, although it's maybe more like cherry picking since that's a statistic and this is just. But the best generalization score are from 2 networks that fail to learn the training set.
But wouldn't he claim that they just memorized the instances? Normally, and neural networks.
Oh, I see what you're saying.
You just memorize the training set instances, and generalization is shit.
So there's only 13 rules that could have been memorized. And
Yeah.
there's 2 to the 10. What is
Uh-huh.
2 to the 10? Is it 1024?
Yeah.
1024. There's 1,024 strings that they're tested on.
Right.
So even if they memorized those 13, the preponderance is stuff that they've never seen before.
Sure, but
Yeah.
part of the issue of generalization, if you just memorize those cases, they don't perfectly represent.
Oh, I see what you're saying. Yeah. So the problem is that in his networks, they just memorize those cases
Yeah,
and nothing
right.
else.
Yeah.
You could say that. I would say in that case, okay, let me show you why I think that's not what happened.
Oh,
Okay. Okay. So back to the third thing about whether these things are truly disjunctive. So 19 learned the training set, but only 18 recognize in the limit. So there's one that learned the training set but doesn't recognize in the limit. Okay, so therefore they're not equivalent. Limit behavior is not necessary for learning the training set. All right, so my argument is that the training set was learned without phase transition. So I mean, this is one of the observations I made. Learning the training set produces worse generalization, and most networks fail to learn one of these simplest rules. Like 80 out of 100 fail to learn that simplest rule. So my argument is that these are all connected. So how are they connected? Okay. So I probably should have waited to play that. So the initial separation when this thing goes is basically by the last digit. Let me grab it. Boop. I'm gonna grab it. All right. I apologize if this is hard to see. At the very beginning of training, what the classification is depends on the very last input in the string. So you may not be able to see this, but these are all strings up to length 5 that end in 1. So this is 0, 1, this is 1, 1, this is 0, 0, 1, up to the top. So it's counting up this way. Over here are all the strings that end in 0, 0, 0, 1, 0, 0, 0, 0, etc. Okay? Before any sort of training happens, the separation is by the last digit. When training proceeds, basically the recency history, what it can remember back in time, increases by a digit at a time until all the strings are smeared across state space. So this is what, I'm going to drag this real slowly, and you can see this. I'm moving it forward. They kind of move to their opposite corners of the boxing ring. And now we're starting to see some interesting separation here. So can you see that, can you see over here that these no longer line up, this one and this one? So this ends in, this block right here, ends in 0, 0. This block ends in 1, 0. This block ends in 0, 0. This block ends in 1, 0. Okay, so that's and it's all this gradient history thing. And if I keep doing this, oh, and you can also see that they're all misclassified right now because I have the class correct across the top. So when it's correctly classified, it'll be green and red, and when it's incorrectly classified, it'll be orange and yellow. So you can see it's starting to classify some things correctly a little bit more. So I've got reds and greens. I'm getting more and more separation. Boom, 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 boom. And stuff just kind of flies everywhere. Boom, 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 boom. Does anybody want to see that in real speed?
yeah, try it one more time.
Shik, 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 shik. Okay. All right, so like what's going on there? So this is what I call gradient descent into chaos. So, yep.
Some of them never became green or red.
That's right. Oh, and thank you for reminding me of that. So let's go back. Let's look at this at the furthest extent of this, because this gives you a sense of what the generalization is really like. So this is the last time step, okay? So all the ones that are green, it accepted correctly. All the ones that are red, it rejected correctly. All the ones that are yellow, they should have been green. And all the ones that are orange, they should have been red, but they were accepted. So as you can see, what's happening here is it's basically shika, 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 slices a hyperplane dividing line between these cases, everything on this side, it's saying, okay, that shouldn't be green, and everything on this side, it says, oh, that should be, it classifies as red, and you can see it screws it up. And across the top, you can see it got 9 correct, 9 of the green ones, so 9 correct accepts sorry, let me use this. For the rejects, it got 10 correct, and you can see ones that it was supposed to accept and then didn't. There's 21 of those, and ones that was supposed to reject and didn't, there are 22 of those. So it's really pretty bad. Yep. Okay. So, so this is what I call gradient descent into chaos. So the gradient descent, and I'm going to kind of explain the mechanism of how this happens, but I don't have a highly quantitative thing to show you. The gradient descent produces these fractal dynamics using this training regime, using his special truncated gradient descent. The fractal dynamics smear points across the state space. They smear them across. So at that moment, theoretically, you can see it as far back in time as you want to, because they're almost kind of randomly scattered around. But the bad thing is that you can't throw a hyperplane across them and divide them evenly because they're just randomly scattered around. So if a hyperplane could separate them, then you've learned the training set, but it's actually due to chance. So 100 times, so there's only 13 rules I have to learn. 18 times out of 100, I can throw them up in the air, they ran around randomly, I can throw a line across it, and I can actually divide those 13 into correct and rejects, okay? But that's just due to chance. I have to do it 100 times, and it only happens 18 times that I do that randomly. So that's the problem. So why does this happen? So making chaos is like making bread, okay? So everybody, I don't know, well, maybe not everybody's familiar with bread, but you have like this dough that you're kneading, and you stretch it out, right? And then you fold it. Stretch it out, and then you fold it, right? So imagine our state space, our 0 to 1, right? And we have these like points in there, or like our kind of final output classes that you just saw in the animation. We stretch it, right? We separate into their 2 corners, and then we fold it. And when we fold it, some things that were far apart become close, and some things that were close become far apart. And you do that over and over again. So here's an example of what that looks like. So I've got 1, 2, 3, ABC up here. I stretch it, it gets long like this. I fold it. Now 6 and 7 are still close to each other like they were before, but now like 1 and C, which were the opposite ends, are now close to each other. And I can stretch, and then I can fold, and then I mixed up again, right? So it's basically like I'm mixing stuff. And it's a deterministic process, but I'm getting something that looks really random. So how does this work in a neural network? So the weights stretch stuff out. Like here's an example, like the weights are just a matrix, right? And this is kind of a hokey like identity matrix 3 and 2. So you can see when it stretches it out, it's actually more of an oval. If I had done 2 and 2, it would still stay a perfect circle. So that's an example of kind of stretching stuff. If you make one of these weights negative, which I think turns out to be really important in this process, not only do you get a stretch, but you can see that points over here in the original shoot over there, right? So it's like, they're crossing each other. So you get this stretching effect through these weights. So as soon as the network has learned enough that these weights get big, you get some serious stretching. Then the sigmoid folds or remaps these big weights down to the interval constrained by 0 and 1, because it doesn't matter. Like I could be over here with 6 with my weights, right? But if I'm at 6, it's just going to map me to something really close to 1. So that's the fold. And so that's basically, it's kind of stretching stuff out and then forcing it back into this little space. And that's what's happening again and again. So are these actually useful? So, my hope was when I first started replicating this work that it really was useful, because what you could do is have an infinite amount of memory. You could kind of leverage the structure of these fractals to store as much information as you want, because storing information in neural networks has always been an interesting and hard problem. And I would say, oh, okay, so you can actually do this thing, but you can't really extract that information very well using clustering, because no matter how small your clusters are, your cluster is going to contain points that are supposed to be there and not supposed to be there, because it's all this random stuff. So, and if you wanted to make use of this, if you wanted to have this fractal space and actually partition it up using a ton of hyperplanes, kind of like we did at the beginning where we separated, the red ones around the outside from the blue ones in the middle, you would need so many nodes to basically carve out all of these arbitrary shapes around stuff that I'm not sure that you've actually gained anything. So just to kind of summarize it, this might be my last slide. So I actually feel like I succeeded in replicating Pollock, but the interpretation that I came up with is very different from his interpretation. He made this interpretation of learning and phase transition, and I did this and made the interpretation of actually something really funky happened here with a random, essentially a random process, and that random process produced a behavior that seemed rule-like, and so a human observing it assumed that it was rule-like, and that's what we see. So just to kind of point out some dangers here that I think people now would immediately recognize: having really small training sets, right? Having a weak evaluation, like you didn't really have a testing set, you basically had a training set and then a bunch of ones. And then having models that are kind of black box models where you really don't understand exactly what they're doing. You kind of treat them like a black box, and that's really dangerous because sometimes a black box model is doing something that's interesting, and sometimes a black box model is just doing something really goofy, and you just think it's doing something awesome. So that's it. And I'm sorry I kept you guys over. I blame Bill Gates. Any questions?
Just one question. What do you consider a rule?
Yeah, I slipped into that terminology because that's actually what I used in my thesis. But so these individually, you could call these rules.
Okay,
So like 3 1s
yeah,
are
so they're tiny cases.
0 1s are, yeah, they're basically cases.
Yeah,
And I call them rules, and yeah.
okay. All right.
Anybody else? Yep.
I'm trying to make connections to, so the fact that the most interesting finding was that, was that people who, the learning was not related to what you call generalization.
Right.
Is that saying the same thing? I'm trying to kind of tie it to the text conversations. Is that the same thing as saying if you stick too close, like people, like learners who stick too close to the text base, just sort of memorizing facts, the thing that's in front of them, are typically not those that are able to transfer that knowledge to something else?
I think that you could make analogies like that. That would be very fair.
So is it that it's not really learning, it's just remembering?
So, and this is, I think, similar to the question that Art asked, like, oh, you've just memorized the training set. And so I would actually argue that that's not even what happened. I would argue that it's totally random, and that literally it's just like, let's throw a bunch of stuff up in the air and throw a line across it, and sometimes everything's on the right side of the line, and sometimes it's not. It's almost like that. Whereas what you're talking about, and I think what Art's talking about is that there was actual learning, but it was the kind of learning where the function that it was learning was, when you see this specific thing, output that. When you see this, output that, right? And there was no rule to handle a case where if you like this ended in an extra 0. Like if that was just not part of the actual mechanism of learning. And so that's a fair alternative interpretation. I don't think that's what's happening here based on the kind of chaotic dynamics and some of the other things. I would need to do a much deeper analysis, I think, to have really strong support against that claim. I mean, I did this like 15 years ago, so don't expect it. Anybody else?
I just have one other
Uh-oh.
question. It's the point where a 1 occurs that's important, right, in this? So if you had a oneness detector, whenever that happens, it has to do this stretch and fold operation.
Right, so they're really both important. But they're important for different reasons. So I think you're correctly focusing on the 1, because the 1 is what you need to keep track of.
Yeah.
But you need to learn to ignore the 0. You see what I mean? So you've got to make sure that when the 0 happens,
You don't do
you
anything.
don't do anything, but when the 1 happens, you do something intelligent. And there's actually, so now I'll say something that I omitted from the talk. So one way of thinking about storing these things is to think about this space, right, of hidden unit states. And you basically say, well, if I end up in a state over here or over here, like this is accept and this is reject. And a lot of people who originally did this work, this is what they were going for because it had the best analogy towards that finite state machine that I showed you. Okay, but there are actually very interesting alternatives that I think could pan out to be useful. The problem is actually having a learning algorithm that can find them. And so this is something that he says in his paper that I think is just really nice and very worth following up. So let's say that I've got a node, a hidden activation node, just a node by itself. And I've got 1 here. Sorry, I just want to -1, 0, 0.5, -0.5. Okay. If I want to store the parity, I can do it in a single node.
Yeah.
I can do it by every time I see a 1, I could basically map it back, map it one way or the other way. Basically by either dividing iteratively or multiplying iteratively and using those opposing operations or adding or subtracting or whatever, as long as they're opposing operations. And then your criterion at the end is to say, am I at 0 or not? If I'm at 0, then it's say even, and if I'm not at 0, then it's odd. So you can actually there's other ways of solving this problem that don't have this finite state automata kind of feel. But then the thing is, how do you actually learn that using gradient descent? And I think that's a question that nobody has solved yet.
I see. Interesting.
Thank you for asking that question. Thanks, Jack.